Welcome back to Toto Physics. This video is all about average velocity. Average velocity tells us, on average, how fast an object moves in a given direction. Because direction is important, this is another vector quantity. To denote average velocity, we use the variable nu, which looks kind of like a v, but with a little more style. And we'll subscript this with an average. The arrow on top denotes that this is a vector. From here, we can build the mathematical definition of velocity. We answer how fast by determining a rate. This tells us how far something moves in some amount of time. But how far something moves is just given by the change in position within that elapsed time. And this, as we know from the previous video, is just the object's displacement, delta x, divided by the change in time. Recall that we use the symbol delta to mean change in. Thus, we've arrived at our formal mathematical definition for average velocity as displacement divided by the change in time. From this expression, we see that the dimension of velocity is given by length over time, and therefore it will have units such as meters per second, kilometers per hour, or miles per hour, with meters per second being the standard SI unit. To see why average velocity is a useful quantity to measure, let's consider a set of observed positions for my toon cat Mochi. These tell us where Mochi was at time 0, after 3 seconds, and after 5 seconds. But now what if someone were to ask, where was Mochi at time equal 4 seconds? Well, the answer is, we don't know. Without having explicitly seen Mochi at 4 seconds, we can't know where he was, but we can use average velocity to make a pretty good prediction for where he might have been. Okay, so let's try it. We know that just before 4 seconds, Mochi was at x equal negative 2 meters. We can estimate how fast he must have been going to get to his next known position. The average velocity is equal to displacement over the change in time. This is equal to the change in position, x final minus x initial, over the change in time. X final will be his position at the time 5 seconds, while the initial time was at 3 seconds. This gives 5 minus negative 2 over the elapsed 2 seconds, which is 7 meters over 2 seconds, or 3.5 meters per second. That means Mochi's average velocity was 3.5 meters per second. This suggests that in 1 second, Mochi would move 3.5 meters to the right. Having started at x equal negative 2 meters, this would put him at 1.5 meters to the right of the rock. Good sleuthing, folks. Now that's the predictive power of average velocity. But wait, there is more. Average velocity has a very nifty graphical interpretation, which will make problem solving even simpler. Let's consider a plot of position versus time. If I wanted to compute the average velocity between these 2 points, then according to our definition, we would need to know the displacement, delta x. But we can read that off this plot as the height difference between these. Then we also need to know the change in time, but that can be measured by the horizontal distance between these. And perhaps you can see if I divide these two, as the definition instructs, then we'll have just computed the slope of the line which intersects these 2 points. This is a very important relationship. The average velocity is given by the slope of a line connecting 2 points on a position versus time graph. Let's take a look at an example. An object's position as a function of time in meters is given by x of t is equal to t to the 4th minus 2t squared. What's the average velocity for the time interval between 0.5 seconds and 1 second? We'll begin by plotting this complicated function just to get an idea for what it looks like using a calculator or some other graphical reference. Now let's make a little sketch. It looks something like this. Let's locate the region of interest between 0.5 and 1 second. To compute the average velocity over this time interval, we just need to draw a line between these 2 points and compute the slope of that line. The slope is given by rise over run. We see that the run of this range is 0.5 seconds. To find the rise, we must know the difference between the position at 1 second and that at 0.5 seconds. We can calculate these by substituting these times directly into the function. Then we plug in the numbers, simplify, to find a rise, or rather a fall, of negative 0.5625 meters. We then use these numbers to compute the slope, and dividing we find that the average velocity is negative 1.125 meters per second. We were able to compute this graphically just by finding the slope of a line connecting these two positions. All of this is good, but it leads to one big question. How good is average? Or in other words, is just using an average velocity enough to accurately locate or track an object, especially one as unpredictable as a cat? Stay tuned for answers in our next video.